Good morning, my name is Joshua Winning from Acouso. The title of this paper is Designing with Acoustics, Not After It, Integrating Acoustic Analysis into BIM as a Continuous Design Input. The central question behind this work is quite simple. If the decisions that determine acoustic performance are made inside the building model, why does the acoustic analysis still happen somewhere else? And usually after those decisions have already been made. Consider a private office beside a conference and boardroom. On one side, there is a meeting underway. On the other, someone is trying to concentrate. Whether that adjacency works acoustically is largely determined when the rooms are arranged, the partition is selected, and the ceiling and finishes are specified. Those are design decisions, and they are often made well before an acoustic assessment reaches the project team. So the problem is not that we lack methods for assessing the separation between those rooms. We know how to establish the requirement, evaluate the construction, and consider the room response. The problem is timing. The decision is made during design. The acoustics are checked later. And by then, the most practical opportunity to influence the outcome may have already passed. That timing problem becomes clearer when we look at the conventional workflow. Rooms and layouts evolve, constructions and materials change, and the information required for an acoustic assessment is authored across several design disciplines. An acoustic engineer receives drawings or a model export. We identify the rooms, their functions, map adjacencies between them, interpret partitions, floors and finishes, and reconstruct the information needed for the analysis. Only after that can the assessment begin. The results are normally returned through a report, schedule, or marked up drawing. But while that work is taking place, the live design continues to change. The information being assessed gradually becomes a snapshot of an earlier design. When the design changes significantly, some of that extraction, structuring, and interpretation has to be repeated. So acoustics tends to enter at selected milestones, rather than continuously while decisions are being made. The acoustic knowledge is not missing. The connection to the design process is. There has already been valuable work on connecting BIM and acoustic analysis. Some approaches transfer geometry into separate acoustic tools. Others use computer vision or artificial intelligence to interpret rooms and adjacencies from exported drawings. These approaches demonstrate that automation can remove part of the manual setup. They also expose the remaining limitation. The acoustic process is still working from the information taken out of the design environment. The contribution of this paper is not another conceptual argument that BIM could support acoustic analysis. It is an implemented framework that operates on structured information within the building model. It reads model objects and their relationships, maps them to acoustic criteria, and communicates design stage results. The implementation is the evidence. This is a practical workflow, not a proposed direction. The key distinction is where the analysis operates. Acoustics becomes another discipline working from the same structured model information used by the rest of the design team. Rooms, boundaries, constructions, and acoustic properties remain associated with the changing design, rather than being reconstructed from a separate snapshot. The analysis lives where the design lives. At a high level, the framework can be understood as inputs, transformation, and outputs. The inputs come from the building model. Rooms provide the function and geometry. Boundary elements provide their location and construction. Materials provide the surface properties required for room assessment. The framework then transforms the model information into acoustic meaning. It interprets the relevant spatial relationships, maps room uses to acoustic criteria, and compares those requirements with the design. The outputs communicate what the design requires and where it needs attention. That includes required acoustic ratings, indicative compliance, and identified shortfalls. The framework has been implemented within Autodesk Revit through its application programming interface. That allows it to read project information and communicate the resulting acoustic feedback through the building model itself. The paper documents the framework using a simplified 14-room office model. That scale made each stage and each figure clear in the printed format. For this presentation, I want to show the same workflow in a larger context. This model contains 3 stories and 92 rooms. At this scale, the information is distributed across a model that is more representative of project scale coordination. I will now move into one floor and follow a single design decision through the analysis. Before the analysis is run, the existing Revit model needs an assessment basis and the acoustic information required by the framework. For this assessment, I selected the AAAC Commercial Building Acoustics Guideline, which is commonly applied to commercial fit-outs here in Australia. That provides the room use categories and acoustic criteria. Preparation then involved assigning those categories to the rooms and associating acoustic properties with the constructions and materials. Reviewable AI-assisted suggestions accelerated part of that work using context already available within the model. Starting from the existing Revit model, that acoustic preparation took approximately 10 minutes for this 92-room example. That is specific to this model, not a universal benchmark, but it illustrates the change in scale. The engineer is not rebuilding 92 rooms and their relationships in a separate analytical model. With that preparation complete, the first output is the acoustic separation requirement. Once the room use categories have been assigned, the framework examines each adjacency and derives the required acoustic separation. Here, a conference and boardroom adjoins a private office. The guideline uses the source activity of one room and the noise tolerance of the receiving room, so the adjacency is evaluated in both directions. With the conference and boardroom as the source, the required weighted level difference, or DW, is 50. In the opposite direction, it's 45. So the higher value governs, and the intervening partition requires a DW of 50. The governing requirement is marked on the intervening partition. The line color communicates the required performance, not yet whether the proposed construction passes or fails. And across the model, requirements range from DW30 through to DW60. The complete floor plan can therefore be marked up systematically from the room uses and adjacency relationships, following the same logic as an acoustic report markup. Once a requirement has been established, it can be compared with what has actually been specified. For a partition, that means comparing the required DW derived from the adjoining room uses with the acoustic performance assigned to the intervening construction. This view communicates indicative compliance. Blue identifies elements or rooms currently meeting the selected criterion. Red identifies where the design requires attention. The assessment is not limited to one acoustic question. The framework can also assess airborne and impact requirements through floors and reverberation time within rooms. These are different outputs, but each begins with the relevant classifications, constructions, and material properties. This is design stage feedback. It does not replace detailed verification or professional judgment. Its value is that it identifies where an acoustic question requires a design response. To make that feedback tangible, we can focus on one shortfall rather than the entire building. For this office, the applicable RT60 criterion is 0.8 seconds. The chart shows the calculated values by octave band with an initial overall RT60 of 1.78 seconds. That identifies a shortfall. The result does not select a design solution. That remains an engineering decision, informed by the room use, available constructions, coordination requirements, cost, and constructability. For this example, I selected 10 square meters of perforated gypsum ceiling. That treatment increases the acoustic absorption associated with the room surfaces. When the assessment is updated, the overall RT60 reduces from 1.78 seconds to 0.62 seconds, bringing the room within the 0.8 second criterion. The sequence required no export and no reconstructed analytical model. We identified the shortfall, made the design intervention, and reviewed the updated result. In the paper, the framework results were consistent with those produced through conventional hand and spreadsheet-based calculation workflows. That supports the analytical consistency of the approach. However, these outputs remain indicative, design stage feedback rather than final verified compliance. The important change is not simply the speed of the calculation, it is the timing of the feedback. So far, I have shown a standards-based workflow from requirement to design change. Beyond this paper, ongoing research is extending the framework into geometrical room acoustics. This is geometrical acoustic ray tracing performed and visualized within Revit. The developing implementation uses these ray paths to support room acoustic calculations. The model geometry and its assigned acoustic properties become the analytical inputs without exporting and reconstructing the room in a separate analysis environment. The work is ongoing, but it demonstrates how the BIM native framework can extend beyond standards-based assessment into room acoustic analysis. So what does this change about acoustic practice? Primarily, it changes where the engineer spends their time, but it does not remove the acoustic engineer. A meaningful share of the conventional assessment is identifying rooms, mapping relationships, and preparing information before the specialist judgment begins. Reducing that repetition creates more time for the work that actually requires expertise. That means interpreting the result, understanding when a minimum requirement should be exceeded, selecting a solution that works with the architecture, services, cost and program, and recognizing where an indicative result is not enough. The role does not shrink, it sharpens. There is also a broader consequence. When the setup cost is lower and the feedback is available earlier, acoustic considerations can enter more projects and more design conversations, including those where specialist input might otherwise arrive only at a late milestone. The productivity benefits matter, but the larger opportunity is to move acoustic judgment closer to the moment when the project team can still act on it. So to return to the private office and conference and boardroom example, we already know how to establish the acoustic requirement. We know how to assess the construction, and we know how to improve the room response. The limitation is that the knowledge is too often applied after those decisions have already been made. This presentation has shown an implemented framework applied to a project scale model and used to complete an acoustic design iteration. Whether we are assessing compliance or visualizing how sound may travel through a space, the opportunity is to make acoustic knowledge available while the rooms, partitions, and finishes can still change. The timing of acoustic input determines what it can achieve. Thank you.